Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for January 16th, 2013.
On this week's show, Mike Cumbo steps down as head of Idex's Optics and Photonics platform, a laser pill boosts in-throat imaging, a phased array of thousands of emitters lets chips steer light, and we speak with another Prism Award finalist, Princeton Instruments.
Mike Cumbo's departure from Idex is an amicable one, he told me last week in an interview. Cumbo spoke with me from Idex's Optics and Photonics platform headquarters in Albuquerque, where he had spent the day working with his successor, Jerry Yurkevich, to make the transition as seamless as possible. Yurkevich is a former vice president of PerkinElmer's optoelectronics division and is coming to Idex from his position as CEO of industrial tools maker Boltech Mannings. Cumbo, who was remaining at Idex as an advisor through the end of February, told me he plans to stay connected to the optics and photonics industry and is planning to pursue more innovative things from the private side, beginning full-time in March. According to his LinkedIn page, he is searching for high-tech small business ownership opportunities, and among the acquisitions he will consider are private asset sales, spin-offs, divestitures, and restructured startups.
So we will still see him at industry events?
Yes, I asked him. He has been involved in optics and photonics for most of his 30-plus year career, and he plans to stay connected. In fact, you and I will be talking with him about industry trends as part of our webinar on the topic next month.
Yeah, and I actually interviewed him and other industry leaders for Photonics Spectra's January Trends issue. In the webinar, we're going to be talking about lasers, optics, and imaging and where we see those sectors heading in the next year.
And you can register for the free webinar at photonics.com/webinars.
Physicians may soon have an easy and painless way to screen the esophagus for precancerous cellular changes thanks to an inch-long device that provides detailed imaging of the upper gastrointestinal tract. Developed at the Wellman Center for Photomedicine at Massachusetts General Hospital, the system includes a pill-sized capsule containing optical frequency domain imaging technology, a rapidly rotating laser tip emitting a near-infrared beam of light, and sensors that record light reflected back from the esophageal lining. Advantages of the technique for detecting Barretts Esophagus, which is a precancerous condition caused by chronic exposure to stomach acid, include that it doesn't require patient sedation, a special setting or equipment, or even a physician trained in endoscopy. The laser pill is attached to a string-like tether. After the patient swallows it, surrounding muscles contract to carry it down the esophagus. When it reaches the stomach entrance, it can be pulled back up by the tether. In tests, physicians operating the system image the entire esophagus in less than a minute. A procedure involving 4 passes, 2 down the esophagus and 2 up, could be completed in about 6 minutes. A typical examination requires a patient to stay in the endoscopy unit for about 90 minutes. Detailed microscopic images produced by the system revealed subsurface structure not easily seen with endoscopy and clearly distinguished the cellular changes that signify Barrett's esophagus. More studies are needed to see if it can be used to prevent esophageal cancer or to discover it at an earlier, potentially curable stage.
An array of 4,096 optical antennas built on a single silicon chip can steer light in arbitrary directions, holding promise for applications such as holographic televisions and medical imaging devices. Although the concept of such phased arrays of antennas goes back more than a century for radio transmitters, scientists recently began applying this model to optics. Optical wavelengths are much smaller than radio ones, so the antennas have to be fabricated with high accuracy at the nanometer scale. No two-dimensional tunable phased array had been built on a chip before, and previously the largest non-tunable array had only 16 antennas. Scientists at MIT's Research Laboratory of Electronics developed a 64 by 64 grid of antennas on a single silicon chip that takes in laser light, knocks it slightly out of phase to produce interference patterns, and then re-emits it via the nano antennas etched into the chip's surface. The MIT team also created an 8 by 8 grid of antennas. The phase shift these antennas produced is tunable, so the chip can steer light in an arbitrary direction. In both chips, the design of the antenna is the same. In principle, they say they could have built tuning elements into the antennas of a larger chip. However, there would have been 4,000 wires coming off the chip, and that would be way too many to solder. Wiring limitations mean that even the smaller chip is tunable only a row or column at a time, but that's enough to produce some interesting interference patterns that demonstrate that the tuning elements are working, they said. The study appeared in Nature.
Today we're introducing you to another Prism Awards finalist, Princeton Instruments. Their isoplane spectrograph is vying for the top honor in the Detectors, Sensing, Imaging, and Cameras category. The product is finding some interesting biological applications, and Melinda spoke with applications specialist Brian Smith about the paper he's going to deliver at the BIOS conference at SPIE Photonics West.
The paper I'll be discussing is work that I've done in collaboration with Jason McClure here at Princeton Instruments and with Dr. Dan Heller, who's a principal investigator at Memorial Sloan Kettering Hospital in Manhattan. And the work I'll describe is using the isoplane to look at fluorescence spectra of carbon nanotubes. And what's really interesting about this work is that what Dr. Heller has done is he takes his carbon nanotubes, wraps them in protein or DNA or what have you, and then sneaks them through the cell membrane into actual living cells. Alternatively, there's a needle that can be used to inject carbon nanotubes into living cells, and then once the nanotube's in the cell, you can hit it with a laser, watch the nanotube fluoresce, and look at the fluorescent signature. And what's interesting about that is that we're finding that the carbon nanotube fluorescence spectrum is sensitive to the chemistry inside the cell. And different types of cells will give different carbon nanotube fluorescence spectra signatures. And ultimately the goal here is to see if a nanotube inside of a cancer cell will give a different fluorescence signature than a carbon nanotube inside of a healthy cell. And then in that case we could use the fluorescence signature of the nanotube as kind of a beacon indicating whether there's cancer present in a tissue or not. And so far what we've managed to do is we've gotten really good images of cells using the isoplane. We've gotten really good images of nanotubes in cells, and we've gotten some excellent fluorescence spectra of the nanotubes inside of living cells.
So what's next for that research?
I think probably variations on a theme. Certainly there are more different types of overcoats we can put on the nanotubes to see how well they get into cells and how it affects their spectral signature. Certainly there are more in different types of cells that we can study, and also I think perhaps something in vivo or in situ might be interesting to try as well.
And this is for diagnostics, not treatment?
Certainly diagnostics would be the initial application for something like this. In terms of treatment, maybe long-term pie in the sky, I can foresee possibly using these nanotubes in vivo at a tissue site to perhaps be able to tell us whether there's cancer present or not.
Great. Thank you very much.
Thank you.
That's really interesting. I'm looking forward to hopefully attending that talk at BIOS.
Yes, we'll both be at the entire conference, both BIOS and Photonics West this year. So if you see us on the conference floor, just step over us. We're just taking a short nap. I'm sure we'll be tired.
No, really, be prepared for hard-hitting questions in the technical talks. Well, that's it for this edition of Light Matters, Photonics Media's weekly newscast.
Write to us with your comments or questions at lightmatters@photonics.com.
Thanks for watching, and we'll see you next week. Or on the conference floor. Maybe you'll see us.
You may see us before we see you.
Yeah. Just give us a nudge, wake us up. We're good.